Okay, so this is Screencast 1.1. This is going to be covering chapters 1.5, 1.5, and 1.7. 1.6 is just kind of on solving problems. It gives you an idea of why you need to show your work and learning to solve problems systematically. That's something I can leave to you to read. Chapter 1.4 in your text, this concept is significant figures and calculations. So if you're filling out your VCEE as you listen to or watch this, let's talk first about vocabulary. First vocabulary term, obviously, is going to be significant figures. Significant figures are digits, sorry about that, digits that help us understand the precision of a measurement. And you might wonder, why the heck do we even use significant figures? Why are they important? Well, I'll let you know that sometimes they're not important. When you are just solving a problem for yourself or trying to come up with an estimation of a number, significant figures are not important. When you are dealing with measurements, like we often do in science, they are important. For example, in math class, you might look at this number, and in math, you might not turn that into a decimal, or you might write it as a repeating decimal. Well, we don't have repeating decimals in science because very often we are looking at this, 1/3 of an inch. Well, if you can exactly measure 1/3 of an inch, you probably can't actually because your ruler isn't that precise. So you're going to report it to the number of decimal places you can actually measure it to. So we would round that to say to the 100th of an inch, because that might be how the ruler is marked. So really what we're doing by recording significant figures is we're communicating to our reader the precision of the instruments that we used. So there are some rules when you're trying to count significant figures, and these rules are listed in the reading if you want to review them, but I'm going to list them here in sort of a shortened version. The first rule is that any integer that is not zero, so non-zero numbers, always count as sig figs in a measurement. Okay, they always count as sig figs in a measurement. Second rule is that zeros count only in certain situations. The first situation is if they're captive. What that means is if they're trapped between two other numbers. Okay, so if they're trapped between two other numbers, they count. For example, 1.02. That zero there is trapped between a 1 and a 2. It is therefore a significant figure. It counts when we're counting how many sig figs something has. 20003. These three are all trapped, so they count as significant figures. This number over here would have 3 sig figs, and this one has 5 sig figs. Okay, so zeros count only if they're captive or if they are to the right of a non-zero integer in a number with a decimal place, or with a decimal point. Okay, so an example of that, I'll give you a counterexample first. This number has 3 zeros to the right of a non-zero integer, but there's no decimal point, so that has 1 sig fig. This number, which you may think is the same, a mathematician might think is the same, but a scientist knows has a completely different precision, has 4 sig figs because there's that decimal point there and the numbers are to the right. This number has zeros that are trapped and zeros to the right, so it has 1, 2, 3, 4, 5, 6, 7 sig figs. This number, here's a tricky zero. This zero is not trapped. This zero is not trapped. We'll add another one just to make it a little trickier. So they don't count, but 1, 2, 3, 4, this one's to the right of the numbers, so it does count. That's 4 sig figs. Okay, so to recap, non-zero numbers like 1, 2, 3, 4, 5, 6, those always count. Zeros only count if they're captive or if they're to the right of a non-zero integer in a number with a decimal point. Okay, all right. So that's counting sig figs. And I've given you several examples of those. If you want more examples, you can go look in the reading. There's a third rule, and that has to do with exact numbers. Exact numbers, examples of those would be things like 1 mole equals 6.022 times 10 to the 23rd atoms. Or 1 inch equals 2.54 centimeters. When we're looking at a conversion factor, we can assume those are exact numbers, okay, because we're giving a conversion there. Exact numbers have infinite sig figs. So how many sig figs does this have? Infinity. How many does this one have? Infinity. Okay, so everything, where this comes in is when you're having to do math with sig figs. So that's my next step for you, is what to do when we have math and sig figs. So, rules for math. Let's see, there is one rule. One rule for doing math, and by math I mean adding, subtracting, dividing, and multiplying with sig figs. That rule, the golden sig fig rule, is that your answer can have no more sig figs than your least precise measurement. I'll give you some examples of what that means. Here's the first one. This is from your book. 4.56 times 1.4 equals 6.38. Now, if we look at the 4.56, they're all three non-zero integers, so that has 3 sig figs. The 1.4 has 2 sig figs. What that means is that my answer can only have 2 sig figs. Okay, so when I look at it, over at my 6.38, I'm going to round that to 6.4 because this 8 rounds the 3 up to a 4. Okay, so my answer there has to be 6.4. So that has the least number of sig figs. It's a little bit different when we look at math. The rule is still the same. No more than your least precise measurement. But here's what happens in math. So let's say we take 12.11 plus 18.0 plus 1.103. Okay, when we line these up the way we would in a math class, we see that the least precise of these is 18.0, okay, because it only goes up to the tenths place. This goes out to the hundredths, and this goes out to the thousands. So our least precise is to the tenths place. That means that our answer has to only go out to the tenths place. So when we add this up, I'm going to trust your book and go that this is 31.123. Our answer can only have 3 sig figs. So we have to round it there. This is a 2, so we don't round this up to the next number. So our answer in the correct number of sig figs is 31.1. The rule of thumb is that you need to do all calculations and round when you get to the final answer. Okay, so what's going to happen here is that you're going to find that sometimes you've got multi-step calculations. You need to not round the interim answers until the final answer. So what that might mean is that you need to learn to rearrange equations and isolate the variable before you do any calculating. For example, if you had an equation that looked like this, 3x plus 2y equals 4, well, let's do 24. So if you had an equation like this, and you were solving for x, you would need to isolate x by itself, so 4 minus 24 divided by 3, before you did any calculating, if it were a more complicated sort of equation. We will practice this more when we get to some actual equations in stoichiometry and in gas laws, when this will come up. Okay? All right. So that is pretty much the sig fig rule. The practice problems that I think are most useful in your text when looking at this would be number 16. And this is the end of the chapter. You'll see that you have active learning questions, you have questions, and you have exercises. So 16, 28, and 30. 29 and 31, the answers are in the back if you need additional practice. But these should be how you quiz yourself. Okay, so 28 and 30 are the best, I think, for sig figs. If you want to do some sig fig calculation, then I would look at, let's see, number 36. And I'll post these all on Schoology as well. But 36 is a good one for looking at that because you're going to have to deal with some exponents. You're going to have to deal with multiplication and division. 35 is another good practice with answers in the back. So 35, 36. And I'll post these problems that I suggest that you work through to make sure you can do significant figures in Schoology.